Hello, I just want to do a bit of a comparison with threaded versus non-threaded. Going to use arc and mutex as some more practice. And what I'm going to do is count to 1,000,000. And I'm going to do it by changing the number of threads to 4 to begin with. And what we're going to do is have a loop which basically takes an arc clone of our original number. It creates some new threads. In this case, it'll be creating 4 threads, and basically each thread should be doing about 250,000, then adding it to the total. So you've got the data is shared, i.e. the start number, which we're trying to get up to 1,000,000, that will be shared amongst, or access to write to it will be shared amongst the 4 threads. At the end, I'm just doing a single thread count to 1,000,000 as well. We're using stood time instant now, and then we get the elapsed method. I did a video on that recently, so yeah, that's there for it. So one thing I've noticed is that by using const, it obviously inlines it and speeds it up. So without the const, it was taking about 10 milliseconds for the single thread and about 2 or 3 milliseconds for the threaded version. So if I run it, got 2, got 8. Again, 3 and 11. Might be easier to see if I do it on here. So got 4 and 7, 2 and 10. So each time the multi-threaded version is between 2 and 4 times faster. Okay, so if we go back, I'm just going to edit number of threads. So I forget the command, but I checked a while back and my laptop has 8 cores, and I think you typically use 1 thread per core. Correct me if I'm wrong on that. So we've got 8 threads now, see if it makes any difference. Right. Need to open that. So it's 4 versus 8. 4 versus 8. 3 versus 7. 3 versus 7. Once more. 3 versus 11. So that's typically 3 milliseconds. So sometimes if you use more threads, it seems that there's a slight overhead. So let's change that. Maybe try 6. Got 3 against 8, 3 against 9, 2 against nearly. So it's fairly consistent. It's pretty much 3 versus 7, something like that. So let's set that back to 4. Right, so I'll run it once more, and we'll just look at how we'll take effectively a baseline. Sorry, done it again. Right, it's 2 and 7. So now if we go into main, and I'm going to get rid of that constant. And let's turn off the inline hint, the type hint as well. So instead of 1,000,000 constant, we'll change that to 1,000,000. And we'll do it down here as well. What you should notice is rather than 2 and 7, it will probably creep up a bit. So if we run it again, yeah, 6 and 12, 3 and 11, 4 and 16. So using a constant enables the compiler to effectively do a lot of the work beforehand. Basically, it works the answer out for you when it compiles. 3 and 11, 5 and 10. So using a constant actually almost makes more is almost more of an improvement than using threads. So yeah, let's change that back again. And just remember to do it down here as well. 3 and 8. So with the constant, it's not making a huge difference to the threaded when we're doing multi-threaded, but you can see it makes quite a sizable difference to the single-threaded version. So I just thought that was interesting, and yeah, if anybody's more advanced in watching this, then you probably already know all this, but I just wanted to kind of record this for my own benefit, just to really work through it, and if anyone else benefits from this, then it's good as well. So we used arc and mutex, so we got the arc new with the mutex new inside, like on I've done quite a few, 2 or 3 videos on this now. So then you clone it. And what we're doing is we're sharing the work basically. So that's why we're doing 1 million over number of threads here. So basically we're doing 4 lots of a quarter of a million. And the local result is basically incrementing each time. And then we take the result, which is we take over the lock of the clone. Then we add local result to effectively to our our total result. Total result is what we want to be, which is 1 million. So it doesn't actually know it's counting to a million, really. It just knows that it's doing 250,000 times 4. Um. Yeah, I took off unwrap. I remember that you really supposed to use unwrap when you do handle join. Oh yeah, and I took out print. One of my subscribers recently sort of said some of when I was looking at some timings, whether in benchmarking, whether using print it might actually affect it. So I've just used debug here. 3 and 7, 3 and 7. It's fairly consistent. 4 and 13. I'm using OBS to record this, so yeah, 3. So it's typically yeah, 2, 3, 4 times quicker if we use multi-threading. Obviously, this is just a toy example. So there is a slight overhead for using Arc and Mutex, so I gather, but even so, compared to, I mean, the alternative is if you want something where you've got multiple producers and single consumer, then MPSC. It depends on whether you need to have multiple sort of access to the same piece of data from multiple threads. So yeah, that's just me doing a bit of experimentation on a Sunday afternoon. So yeah, I thought it was interesting just the way it splits up the task. Because most of the examples with Arc and Mutex will just they don't split the task up, so it makes sense to split the task up. Chop it up into 4 jobs and then give a quarter of the job to each thread. Yeah, what else? I was going to say something else. Forgotten what it was. Let me just look at what I've been doing recently, and I might just remember. So, oh yeah, I've also been looking at writing. I'll just show you this. So I've been looking at writing stack generic. I know you're not supposed to use capitals in project names, but never mind. MB, so main. I've actually been looking at writing a stack virtual machine, kind of like a 4th type language stack in Rust. And if you know anything about this 4th stack language, I think it uses is it reverse Polish notation? And yeah, just one useful thing is to use hex decode, because I was trying to do the decoding from a string into bytes. But if you try and do it manually, you have to split it up into chunks of two, and then you have to map those into bytes and so on and so on. So yeah, use if you use hex decode, and yeah, I put all my functions and structs and everything into lib.rs, and then obviously made them public. Yeah, the other good thing was, or interesting thing was that so with the stack, I was building it so that you could either add numbers like an I32 or a hash, and obviously a hash is not just numeric. It's yeah, so it's so what I've used here is a U8, a vector of U8. And then depending on how you want to present it or view it, then you can obviously manipulate it and display it as however you wish with uh, you can display it as hex with you'd put the curly braces with the X in there to display the hex. And then I wrote a function. So if you know anything about Bitcoin, it actually takes a SHA-256, it hashes once, and then it hashes using RIPE-MD168, then it hashes the SHA-256 hash. I was having all sorts of fun with type conversions between U8s, arrays of U8s, and 2vec and so on. So see, it returns a vec of U8, but it actually takes in um, an array of or reference to a U8 array. So yeah, 2vec. If you look at the types there, the SHA-256 actually uses something called a core wrapper, CT variable core wrapper. Yeah, I don't know about that, but it worked. It worked. But yeah, I just thought that was interesting where you can use an enum to allow you to create a stack, and then you can push to the stack. So I've got a function here which is pushing an integer. So where it's integer, the item is a stack item integer, then stack item hash. So two functions. I tried doing it with generics and got in it just got really complicated really quickly. So I think this is probably the optimum way to do it. So yeah, that's that. And